projection, wherein we associate a unique point on the unit sphere in 3 space to a complex number. Or vice versa, actually. We go forward in that process first, but we can reverse it since the assignment is unique. Right, so I think we finished Friday with some observation that inside the unit disk, all complex numbers correspond to the southern hemisphere of this unit sphere in 3 space, and all complex numbers outside the unit disk correspond to the northern hemisphere. Right, so let me just draw this picture again. Here's a unit sphere, supposedly, and I'll draw a plane cutting it at its equator, and I take this point N, the North Pole, right? And how this assignment works, I pretend that this plane that is corresponding to the xy plane, essentially, is the complex plane, right? So let's say I have a number here, z, little z, then I draw a line between n and little z, and where that line, the unique point at which that line cuts through our sphere, we call big Z. Z is the stereographic projection of little z. Sorry, I guess I should make this bigger. Okay, so that was our setup, right? And we had this observation about all these points in the northern hemisphere correspond to the points outside the unit disk, right? Of course, there's points on the plane that are outside the unit disk here too. And then all the points below correspond to everything in here, right? That's just what we were saying at the beginning here, right? And then, of course, on the boundary of the unit disk, that actually coincides with being directly on the sphere, the equator. Okay. Let's make some observations about this geometry that we've set up, how the complex plane relates to this unit sphere, which in this context we call the Riemann sphere, after Bernard Riemann, famous for many mathematical contributions, including the Riemann hypothesis, right, about the distribution of primes. Not much to say here about that, but interesting nonetheless. He was quite the polymath, right? He was good at all types of math. So let's just make some observations here. Let's consider a line through the origin in the complex plane, C, corresponds, or I should say projects, by which I mean projects stereographically onto what? If I take, let's say my origin is here, and here's the point 0, 0, 0, and I take a line in the plane through this point, this line that I just drew lies in C. What does that stereographically project to on the sphere, the Riemann sphere? Think back to what we were just saying.
Would it just be the arc above the line zero, or the line spanning the axis?
So that's close, right? Because remember, this line goes through the origin. So we know that there's points on this line that lie inside the unit disk, and those that lie outside the unit disk, right? So for the points inside the unit disk, we'll get the, sorry, I said that wrong. For the points inside the unit disk, we'll get the lower semicircle, right? And for the points outside the unit disk, we'll complete that circle. Okay, and this drawing is becoming quite muddled, but what you get is a circle on the sphere of the same diameter as the sphere, a great circle. Okay? So a line through the origin in C projects onto a great circle on the Riemann sphere. And of course, a great circle is one with diameter equal to sphere. Okay, terminology from geometry, solid geometry. If we're thinking about this, remember I mentioned at the end of class on Friday that this scheme of associating points in a plane onto points of a sphere comes from cartography, map making, people trying to make a flat map of the globe. So, in particular, these are, we could also call these circles of longitude. Right, the bands that run north-south on the globe. Okay? So conversely, well, converse isn't exactly the right word, but what if I were to consider a circle centered at the origin in C? What would that correspond to? Or I should say project onto. Onto what in the Riemann sphere? Okay, so that is to say, I'm not going to add to this drawing, it's already too cluttered. But if I take a circle in the plane around the origin, what does that project onto? Yeah?
A horizontal circle that's position is based on how far away from the origin it is.
Yeah, exactly. Right, so if I take a circle that has a radius less than 1, it's going to be a band on the globe, a circle of latitude, you might say, in the lower hemisphere. And then if I take something larger, something of radius larger than 1, this will make a circle of latitude in the northern hemisphere. Okay? And this checks out with the fact that the circle of radius 1 is exactly a line of latitude along the equator in the Riemann sphere. Okay? So circle centered at the origin in C projects onto a circle of latitude on the Riemann sphere. Okay. I'll also say this, and maybe you'll have to do this on the next homework assignment, or at the very least, you should convince yourself it's kind of true. And in fact, it's totally true. Angles of intersection of lines through the origin and circles centered at the origin are preserved by projection. By this process of projection. So this is actually the first example of a phenomenon which we will place a lot of value on, which is if we have a transformation that preserves angles between geometric objects, we call it conformal. And this will come back later in the term. That is to say, stereographic projection is conformal. Okay. So you can kind of see everything I've told you just now, right? It's fairly easy to visualize this, but you know, it might be desirable to have some kind of working formula, like an algebraic expression to move from complex numbers into points on the Riemann sphere. So let's try to develop that, and then we'll have more concrete ways of verifying these observations than me just waving my hands at them. Okay? So, all right, let's develop a formula. Okay, so go. Okay, so I think a good place to start is to write the equation of a line through the point N, the North Pole, and some arbitrary point in the complex plane, this equatorial plane interpreted as the complex plane. Okay, so how do we write the equation of a line? This is from Calculus 3, if you took it here. The line through N, the North Pole, and in terms of how it sits in space, remember our cutting plane is the xy axis, right? So the coordinates in 3D of some complex number z are just x, y, 0, right? Because we're in the xy plane. Or that's what we're identifying with the complex plane. Okay, so anybody remember the formula for a line through 2 points in space? A few different ways to write this, but let me just remind you that one of the most convenient ways is to just take a point which you know is on the line. Okay, so that would be our n, right? Because it's the fixed point. We're letting z vary here. So we should start with n being designated to be on our line no matter what. And then what we need is a vector which is parallel to the line. And then we can write a parametric equation of the line. Okay, so given that n is definitely on the line, and we're letting z vary and insisting that it be on whatever line we're constructing, how do we determine a vector parallel to the line that we're trying to construct? Yeah?
So the vector that spans the distance between n and z.
Yeah, it's just the displacement vector from n to z, from n to little z. Okay, so let's just write that down. So we get a parametric equation for the line through the point n and z, given by x comma y comma z is equal to the point that we know the line goes through, n, plus our parameter t times the vector given by the displacement from from n to z. So we take final minus initial, right? Okay, or if we simplify this, right, we can get x, y, -1, and this is a slightly pedantic point, but I'm teaching calculus 3 right now as well, so this is the vector form of this equation. We can also give this in parametric form, that is to say, as a set of 3 equations, right? Just by separating out the components of each of these. Okay, so that is to say, x is equal to, sorry. So you'll remember on Friday I gave you these weird coordinates for R3, where we just use x1, x2, x3, right? And so we can use our standard xy for complex numbers. I'm sorry that I forgot that. So x1 is equal to the variable x that we're letting vary through z times t. x2 is equal to this y value from our complex number z times t. And x3 is equal to 1 minus t. Okay? So, and just to emphasize, remember, t is just a parameter. It's just a real number. So, every value of t gives you a point on this line that we're specifying that intersects both n and z.
Would putting these x1, x2, x3 into our equation for the sphere, would that give us a parametric form for the projection?
It's going to tell us the intersection, right? Yeah. That's what happens when you have equations for geometric objects and you substitute one into the other, then you get their intersection. And that's exactly what we're after, remember? Because the stereographic projection of little z is the point at which this line through n and little z intersects the sphere. So in order to find that intersection, what we'll do is take these parametric equations and plug them into the equation of the unit sphere, centered at the origin. Okay, good. So, what's the equation of the unit sphere centered at the origin in R3?
x1 squared plus x2 squared plus x3 squared.
Yeah, good. Okay. Equations into the equation for the sphere. So, as was just said, here's our equation of the sphere. When I plug in, what do I get? I get xt squared plus yt squared plus 1 minus t squared is equal to 1. Or expanding this, what do I get? I get x squared t squared plus y squared t squared plus 1 minus 2t plus t squared is equal to 1. Okay, which if I just collect terms, I can rearrange this to say that 1 is equal to t squared times x squared plus y squared, that looks like a times, plus y squared plus 1 plus 1 minus 2t. Okay, so let me just subtract 1 from both sides, and then I get t squared times x squared plus y squared plus 1 minus 2t, or if I like, I can factor this out, factor a t out of this, t times x squared plus y squared plus 1 minus 2 is equal to 0, right? I got from subtracting 1 from both sides. So what is this telling me? This implies together the roots are what? That is to say, what values of t satisfy this equation?
T equals 0 is on the left.
T equals 0, good. And there's one other one.
2 over x squared plus y squared plus 1.
Yeah, exactly. We just set this other part of the product equal to 0. That's all for t. Alright, so we get 2 divided by x squared plus y squared plus 1. Now, is just to keep us grounded in the fact that we're working with complex numbers, let's remember that this is just the modulus of z squared, right? Okay, so maybe we're getting somewhere now, right? We have found the values of t where our line through n and little z intersect the sphere. Okay, what point on the line does t equal 0 correspond to? The North Pole, yeah. Therefore, the other point, t, the other root, is where we intersect the sphere besides n, the unique stereo So now to find the coordinates, specifically in terms of the components, the real and imaginary part of z, we just plug that value of t back into our parametric equations. Right? And then our coordinates on the sphere, x1, x2, x3, are given to us by plugging in that value of t. Okay? So plugging in t equals 2 over modulus v squared plus 1 to the parametric equations. To get x1 is just 2 times x divided by modulus of z squared plus 1. Or, if you like to really emphasize that we're working with complex numbers, you might say 2 times the real part of z divided by the modulus of z squared plus 1. Likewise for x2, we just get 2y divided by the modulus of z squared plus 1, or 2 times the imaginary part of z divided by the modulus squared plus 1. And x3, what do we get here? We get 1 minus 2 divided by the modulus of z squared plus 1. I'm going to rearrange this slightly algebraically just to make it look nicer. So firstly, I'll give these two a common denominator, right? This is the same as the modulus of z squared plus 1 divided by the modulus of z squared plus 1 minus 2 divided by the modulus of z squared plus 1. Okay, what do I get here? I subtract 2 from 1. So I just get the modulus of z squared minus 1 divided by the modulus of z squared plus 1. I don't know, if you ask me, one of the main uses of algebra is to put equations in a form that's easier to remember. So hopefully that's achieved here.
Yeah, so we just took a complex number and returned, so a function took a complex number and then returned 3 real value scalars.
Mm-hmm. Yep, that's exactly what we've done. Not only that, but you can check that, in fact, this was how we derived it. You can check that these formulae that we derived for x1, x2, and x3 satisfy this equation. Right? I mean, actually, just by doing what we did, that necessarily must be true. But it's good to look back and see that it's like, oh, well, I didn't expect that to be related to the complex numbers, but yeah, here it is. Okay. Good. Good. Okay. So, okay, just quickly, for example. Little z, and I'm really trying to distinguish my little and capital z. So if it's not clear, let me know. So let's take little z just equal to 1 plus I root 3. Okay, so this corresponds to what capital Z? Compute that for me really quick. Yeah.
2/5, 2 root 3/5, and 3/5.
Yeah. That's exactly right. What's the modulus of this is 2. The modulus squared is 4. So we get 5s in our denominators for all 3 components of this point, capital Z. And then we just have, for the x1 and x2 component, we just have 2 times the real part, 2, and 2 times the imaginary part, 2 root 3. And then, again, the modulus squared is 4, and we subtract 1, so we get 3. So, the only thing I'm trying to point out here is that derivation might have seemed kind of abstract or less useful than it actually is, right? Because we can compute moduli really quickly. And real and imaginary parts are just reading off the complex number, right? So, you know, you can very rapidly convert from complex numbers to points on the Riemann sphere. Good. Okay, so conversely, and this time I mean it. Conversely, given x1, x2, x3 on a Riemann sphere, how do we get the complex number that projects onto that? We have little z projecting onto it by, well, it's a little easier if we go back to our original parametric equations with just the t, right? So we get x is equal to x1 divided by t. Y is equal to x2 divided by t. And here, now we have to specify what t is, right? Because we expressed t in terms of x and y before, but now we're given x1, x2, and x3, right? So t is just given by 1 minus x3. Right? Look back at the parametric equation. I'm just solving for t here. Okay, so it's actually significantly simpler to go from a point on the Riemann sphere to a complex number, right? I mean, it's pretty simple to go from a complex number to a point on the Riemann sphere, but here you don't even have to compute a modulus. You just have to subtract and divide twice. Okay? So, or you could say this all together, or you could write little z. Of course, you'd say, as usual, is equal to x plus iy. Or, in other words, x1 divided by 1 1 minus x3 plus I times x2 divided by 1 minus x3. Okay. Okay. So, right, these are nice formulae. Now let me tell you something that may seem a little bit surprising. That's a slight generalization of what we observed about lines through the origin in the complex plane and circles centered at the origin in the complex plane. We're going to give a rigorous proof of our observation about projection of such objects, and we'll prove more, as a matter of fact. We can make an analogous statement for all circles and lines in the complex plane, whether or not they go through the origin. Okay? All lines and circles in the complex plane C project to circles on the Riemann sphere. Now, notice we dropped some qualifications here. I didn't say they were great circles. They won't necessarily have the diameter of the entire sphere. Yeah. So yeah, it becomes a bit harder to visualize what's going on here, but it's motivated the same way that we observed lines through the origin and circles centered at the origin. That is to say, we won't necessarily have circles of latitude or longitude when we consider the general case. We might just have some random circle at a skew angle on the sphere. Okay? Okay, so the proof is algebraic because I think it's best if you just think about the geometry, and maybe you can draw better than me, than I do on the board or in general. And I think that'll be more convincing to you, but I can show you the algebra, dead to rights. So let's do that together. Okay, so. Here's the general equation for a line or a circle in C. Or circle in C, where as usual we'll have Z be equal to X plus IY. Is given by A plus X squared plus Y squared plus CX plus DY plus E is equal to 0, where we have A, C, D, and E real numbers. Why did I skip B? these squared terms grouped together. Right? If I let them vary, I'm working with an ellipse. If I let the coefficients on x squared and y squared be different, I'm working with an ellipse. Right? In fact, this is the general equation for a conic section. But we're going to restrict our attention to when the coefficients of x squared and y squared are the same, i.e. the circle case. Okay. Great. So now all we'll do is just we'll substitute our last derived formula into this equation for the general circle or line. Okay, so plug in, should say x equal to x1 divided by 1 minus x3, and y equals x2 divided by 1 minus x3. What does that give us? Right, the mess. D times x2 and 1 minus x3 e is equal to 0. Okay. Right, what I'll do here is just multiply through by 1 minus x3 squared, canceling these two terms, these two denominators, right? So, let me see here. Right, so let me just write this down. Recall that x1 squared, x2 squared, x3 squared is equal to 1, right? We're assuming that we're on the Riemann sphere, right? Because we use these formulae. Then this implies, of course, that x1 squared plus x2 squared is equal to 1 minus x3 squared, right? So first I'll clear these denominators, right? So I get a times x1 squared plus x2 squared plus c times x1 times 1 minus x3, right? I'm multiplying through by 1 minus x3 squared. I have one copy of 1 minus x3 in the denominator on c, so I still have one copy in the numerator. x2 times 1 minus x3 plus e times 1 minus x3 squared. Of course, anything times 0 is 0. We're good there. And then by this observation, I'll replace this with 1 minus x3 squared. All the rest of the terms are the same. now, this might seem kind of circular, but let me now divide by a copy of 1 minus x3. Okay, so if I divide by 1 minus x3, I get a times 1 plus x3, right? This is a difference of squares, so I can factor it as 1 plus x3 times 1 minus x3. Then I divide by 1 minus x3, so I'm left with just this binomial. Okay, plus c times x1 plus d times x2 plus e times 1 minus x3. Okay? Again, I can do this because my line or circle is equal to 0, set equal to 0 here, right? So I can do these multiplications and divisions because I cancel on the other side. Okay. So, now notice that we have the same binomial multiplied by a and e, right? So we can collect, oh, yeah, right, yeah. It's not the same binomial, but we can still collect those terms together, okay? So this is equal to cx1 plus dx2 plus a minus e times x3 plus a plus e is equal to 0, right? All I've done here is I distributed the coefficients a and e, and then I'm collecting all the terms with the same variable. That's what I wanted to say before. Okay, so now I'll again call on your knowledge of Calc 3. What is this the standard equation of? In R3, yeah?
Plane.
Yeah, this is just the standard equation of a plane. The standard equation of a plane in R3. Okay. So, now, what is the intersection of a plane and a sphere?
Circle.
It's always a circle, right? So we derived this equation of a plane from the equation, the general equation of a circle or a line in the complex plane. From the general equation of a circle or a line in the complex plane, we derived a standard form equation of a plane in R3. Therefore, its intersection with the Riemann sphere must be a circle. Okay? So, the intersection with this plane and the Riemann sphere is always a circle. Of course, that's true of any plane and sphere as long as they intersect. But we know that this plane we derived and the Riemann sphere intersect because we determined a one-to-one and onto mapping between complex numbers and the Riemann sphere. So we know that this plane intersects the Riemann sphere because it comes from the equation of a circle or line in the complex plane. Okay? Okay, so you can reverse this argument as well and say that any circle on the Riemann sphere corresponds to a line or a circle on the complex plane. Basically, you just have to reverse all the computations we made with the formulae for x1, x2, and x3 in terms of the real and imaginary components of z, right? You just have to do the reverse using the other set of formulae that we first derived. Okay? Okay, so I want you to notice something here. In all the computations that we just did, we excluded from consideration the North Pole, right? Because these formulae are not valid at the North Pole, right? Because remember, n is 0, 0, 1, x3 is 1. We'd be dividing by 0 in these formulae if we allow such considerations. So, note. Just because of the formula that we derived, we would have divided by 0 a lot. You can kind of think of this as a defect of the fact that we chose n to be this fixed point that we would draw a line through to determine the stereographic projection of a complex number z. That's because you need 2 points to specify a line, right? If we just have n, and we're like, oh, where does this go to on the complex plane? Well, we need another point, but we only have n. We said, okay, we're going to choose a point, a line through point n, and whatever other point we're considering. When we consider n, we don't have enough information to determine the line. Okay? So, consider this. You can just draw a sketch. Again, well, actually, I don't want coordinate axes. Sorry. Here's, again, a sketch of my Riemann sphere. Oh, that's really terrible. Let me try again. Let me try one more time. That's better. Here's my Riemann sphere again. So, when I have a really large modulus complex number, like let's say something way out over here, my stereographic projection on the Riemann sphere becomes closer and closer to n. Right? The larger my modulus gets, I get closer and closer to this North Pole. Now, yeah, so let's write that down. As the modulus of z, little z, tends to infinity, projections tend toward North Pole. Okay? So, basically what this suggests is that we can kind of throw in the complex number infinity. Okay? So, we associate n with this new complex number, infinity. Okay, now, you might remember from Calculus 1, there's some occasion to talk about the extended real numbers. I think especially when you start talking about improper integrals. Right? You want to treat infinity like a real number in a certain regard. We're doing a similar thing here, but it's fundamentally different in character because, well, let me let you think about that for a little bit, and I'll say something in a couple minutes, or something we're leading up to now. But think about that while we get there. How is it different that we consider infinity as a complex number versus infinity as a real number? Yeah.
Is that why sometimes in like the literature you see some infinity?
That's a different construction. That's something way more algebraic. The standard notation here is so we have a new set. The extended complex numbers which most often is denoted C hat, which is just all our standard complex numbers union this new thing that we denote by the symbol infinity. And before we go on, I just want to make a comment that, remember at the beginning of the term, lecture 1, we talked about this way of throwing in new numbers to old number systems. That's not what's going on here. We're not talking about doing arithmetic or solving polynomials with infinity. We're adding this in for topological considerations to make stereographic projection more complete. And so it's kind of different. I don't want to say throw in, because we use that terminology for an algebraic construction at the beginning of the term. Now we're just taking the union. We're not saying we're taking linear combinations of complex numbers with infinity, because that doesn't really, doing arithmetic with infinity doesn't make sense, but in terms of having it be approached as a limit makes a lot more sense. Okay? Okay. So, right. So what do we think of when we think of adding infinity to the real numbers? What's the geometric meaning behind that? Yeah.
Going infinitely far in a particular direction like what the x is.
Yeah, right. So in the real numbers, there's kind of two distinct concepts, positive and negative infinity. Right? There's exactly one direction from which you can approach either. Right? So contrast this with plus or minus infinity in, maybe we didn't use this notation in calculus 2, but by this I just mean our union, the set with two elements, plus and minus infinity. We think of these as distinct concepts something like growth infinitely in the plus or minus direction. But in C, whereas infinity in C hat can be approached from infinitely many different directions, right? I could make my modulus huge this way. I could make my modulus huge this way. I could make my modulus huge this way, right? There's any direction I want, I can go out infinitely, and I approach the same notion of infinity. It's not a signed concept. This has some comparison with what we did in homework 1, where we showed that there's no order on the complex numbers, right? If something becomes infinite, it doesn't make sense to say positively or negatively infinite. It just becomes infinite. So, whereas infinity in C can be approached from infinitely many directions. Okay, also what this means is that it makes sense, it makes some kind of topological sense to talk about a neighborhood of infinity. Take this circular cap around N on the Riemann sphere. What does that correspond to?
Complex number that is modulus local to infinity?
Say that again?
There are complex numbers like local, or local, like complex numbers with modulus close to infinity, or?
So, I mean, that's conceptually on the right track, but let's just think of the theorem that we proved before. I have this circle on the Riemann sphere.
Oh, so it's a line or circle.
So it's a line or a circle, and furthermore, the way I've drawn this, it's supposed to be a circle of latitude. So the boundary of this cap that I've drawn is a circle centered at the origin in the complex plane. What about the points in the Riemann sphere in this shaded region, in the cap? Where do those correspond on the complex plane?
Outside of this, because
Exactly. They're the complex numbers with modulus outside the circle that corresponds to the bounding circle on the Riemann sphere of this cap. Okay? So, it is sensible to talk about neighborhoods of infinity which correspond to circular caps on the Riemann sphere. stereographic projection. A neighborhood of N. Circular cap. So, this whole time we've been talking about stereographic projection. It's like, well, this is kind of cool. We have a way to have a three-dimensional representation of complex numbers. But not only that, we've now been able to shed some intuition on what it means and even have a solid geometric picture of what it means to have a neighborhood of infinity in the extended complex numbers set. So, yeah.
Can you do the same thing in terms of the neighborhoods of infinity with circular caps instead of for latitudinal but like longitudinal on like the far sides of the sphere?
So, it all has to do with our choice of point that we fix on the sphere in the beginning to like draw our lines. So, can you have I guess what you're asking is,
Like if we had, using it, if you had, a line in the complex plane, would it be like everything on the side of that line that is not the side that contains the origin would make...
would contain the point infinity.
Okay.
Yeah, right. So, like, for example, we had real part of the set of the complex plane, the subset of the complex plane cut out by the real part of Z is strictly greater than 0.
Yeah.
Right? That contains infinity.
Okay, and if we were to like stereographically project that, would it end up making a circle on like the left or right side of the unit?
Yeah, the
Right, cap-ish kind of thing?
it's not a hemisphere, but I guess it is a hemisphere, but not the way we talk about it on the globe.
Yeah.
Yeah, it's a vertical hemisphere.
Yeah.
Right? Yeah.
Okay.
Yeah. Yeah. So this is an example of a general phenomenon where we take something which is unbounded, the complex plane, and by adding a single point and making the right definition of what it means to have a neighborhood around that point, we can make it closed and bounded, i.e. compact. Okay? So for those of you who might want to continue in topology, let me just remark. This is an example of something called one-point compactification. That is to say, if the space is nice enough, you can add a single point and say how it behaves in regards to what neighborhoods it has, and then that new space that you created will be compact, which we'll get a sense of why is important. We defined compactness on Friday, right? Is that right? Closed and bounded? Yeah. So, good. Okay, so with this in mind, let's talk about how we can compare distances in the complex numbers with the distances in 3 space for the corresponding points on the Riemann sphere, right? We would like to have a relationship between the distance in the complex plane and the distance in space between points on the Riemann sphere. Okay, and this is related to, I told you before that this map, stereographic projection, preserves angles between lines and circles. So a natural question for a geometer to ask is, like, okay, so what does this process of stereographic projection do to distances? And because there's two distinct notions of distance in these. And actually, I'll just give you a preview here. What we'll do is we'll interpret the distance in the three-dimensional setting in the complex plane. Okay? So, here's the theorem. So let's take little z and w in the complex plane, and capital Z and capital W. I'll put wings on it to make it capital. They're projections. Onto the Riemann sphere. Okay. And the distance in R3 from Z to W is given as, okay, so we'll write distance, or dist, for the distance in free space is just given by 2 times the modulus of the difference from little z to w divided by the square root of the modulus of z, little z squared, plus 1 times the square root of the modulus of little w squared, plus 1. Okay, so let's derive this. Again, there's a geometric insight you can have here, and I'll probably include that on the homework as well. But for now, let's do the boring part together, the algebra. Okay? So, first of all, just for convenience, let's just call D the three-dimensional distance between Z and W, just so we don't have to write that over and over again. And then let's set down some coordinates. Let's use x1, x2, x3 for the coordinates of Z, and the coordinates of W we'll call y1, y2, and y3. Okay. So, just the normal Euclidean distance in 3 space is computed as follows. Just like any other Euclidean space, right? It's the difference of each component squared added together. Okay, so we get x1 minus y1 squared plus x2 minus y2 squared plus x3 minus y3 squared. Which I'll just expand. Right, I get x1 squared minus 2x1 y1 plus y2 squared, I'm sorry, y1 squared. Plus an almost exactly the same expression.
Should that be should that be the square root of all that?
Yeah, it should be the root of that, right?
Oh, right, I'm sorry.
No, yeah.
What I meant to say was this. Because this is, just so we don't have to write the square root over. But also it makes the conclusion happen faster. Okay, good. Thank you for that. Okay, plus our last term, also analogous, almost exactly the same except for the subscripts. Okay, so I will then collect my terms and factor, right? So you get 2 times 1 minus x1 y1 plus x2 y2 plus x3 y3. Okay, so what did I do here? How did I get from this step to this step?
Is it by the fact that x squared plus, or x1 squared plus x2 squared plus x3 squared is 1? And same thing for y1, y2, and y3?
Yeah, exactly. When I add these 3 things together, I get 1. Because my points, capital Z and W, were on the Riemann sphere. And likewise for y1 squared, y2 squared, and y3 squared. So I get 2 copies of 1. And then I have a 2 in front of each of these coefficients. A negative 2, actually. Okay. Okay, so, then let's let z equal x plus iy and little w equal to u plus iv. And we just use the formulae for converting from C to the Riemann sphere. And what do we get? This implies that this term, I'm going to omit the 2 for a second, again, just out of convenience. It's the part of the equation that we care about. So I'll say 1 minus x1, y1, x2, y2, plus x3, y3 is equal to, so I have formulae for each of these. For each of the x1, x2, x3, I have formulae in terms of x and y. And for y1, y2, y3, I have formulae in terms of u and v. And put those all together. Okay? So I get 1 minus 4 times xu divided by the modulus of z squared plus 1 times the modulus of w squared plus 1. Right? Minus 4 yv over the same thing, the modulus of z squared plus 1 times the modulus of w squared plus 1 minus the modulus of z squared minus 1 modulus of w squared minus 1 divided by the same thing. The modulus of c squared plus 1 times the modulus of w squared plus 1. Okay? All I've done is just apply my formulae for x1, x2, x3, and y1, y2, y3, and multiplied everything together. Okay, so let us make the simplifications necessary. So, minus 4x u minus 4yv minus divided by this. Okay, so let's just FOIL these out. D squared, W squared, plus 2. Right, not 2. Plus modulus of D squared plus modulus of W squared plus 1. So changes here. Minus modulus C squared, modulus W squared, minus modulus C squared, minus modulus W squared, plus 1.
Shouldn't those squared be outside the modulus?
Yep. But of course, that must be true anyway, right? Since the modulus is multiplicative. Okay, now we get some cancellation, right? This cancels with negative this. 1 cancels with negative 1. Good. So, what do we get? We get 2 modulus of z squared plus 2 modulus of w squared minus 4xu minus 4yv Okay, what do we do now? Might seem disheartening, but now let's express this in terms of the real and imaginary parts of z and w, both these. Okay, so we get what do we get? We get 2x squared plus 2y squared plus 2u squared plus 2v squared minus 4xu minus 4yv all over the denominator we've been carrying this whole time All right, now I have the middle term of some binomial foiled, right? I can put, let's say, this term, and this term together, and factor that, right? So now I get 2 times x minus u squared, right? I factor 2 from each of these terms, and then I get x squared minus xu plus u squared, which is just x minus u squared. Same thing for my remaining terms. Right? I just get 2 times y minus v squared. Okay. Maybe we're making a little progress. After all. So I have x minus u squared. I'll factor a 2 out of this. And I have x minus u squared plus y minus v squared. What does that remind you of?
The modulus of u minus v.
Yeah, it's the modulus of the
Z minus w.
of z minus w, yeah. Okay, so this is just 2 times the modulus of z minus w over modulus of z squared plus 1 times modulus of w squared plus 1. Okay, so plug this back into my original equation for d squared. What do I get? I get 2 times 2 divided by z minus w all over the modulus of z squared plus 1 times the modulus of w squared plus 1.
In the top, it's the modulus of z minus w squared.
Yeah.
Squared, yeah, you're right. That's true, sorry. There's no square root there, so it's squared. Okay, so now I take the square root of both sides, right? So I get just a single 2, that cancels, and these become square roots. And that's what we were trying to show, right? Let me write the conclusion more cleanly. Okay, so b 2 times the modulus of v minus w divided by square root of the modulus of z squared plus 1 times the square root of the modulus of w squared plus 1, which is just what we were trying to show. Okay? So, let me just make a few closing remarks. This is called the chordal distance. From little z to w, which we denote chi of z comma w, which is just the three-dimensional distance between their stereographic projections, which is just given by this formula that we just proved. Okay, so the important thing about this is that this is a distinct from Euclidean distance in the plane, but it's still a metric, which means that it obeys all the same rules as Euclidean distance does. Chi is a metric. Meaning that chi of z1 comma z2 is less than or equal to chi of z1 comma w plus chi of w comma z2 for all z1, z2, and w complex numbers. Right? This is the triangle inequality. Okay. 2 chi of z comma z is equal to 0, all complex numbers z, just like in the Euclidean metric, right? The only thing with distance 0 to z is z itself. Okay? And 3, it's symmetric. The chordal distance from z to w is equal to the chordal distance from w to z. Okay, that's nice, but even more amazingly, we can use this notion of chordal distance to say what it means to define a distance from a complex number z to the point infinity in the extended complex numbers. Okay? It doesn't make sense in the Euclidean metric, but with the chordal metric, i.e., the thing that we just derived, which is based on the geometry of the sphere in 3 space, where the point infinity has a concrete realization as the North Pole, we can say what it means for a point, a complex number z, to have a finite distance from infinity. Okay, so let's derive this for the last thing we do today. Say we want to compute the chordal distance from some complex number z to infinity. Well, what we'll do is we'll take the limit as the modulus of w goes to infinity of the standard formula for chordal distance, z minus w over the square root of the modulus of z squared plus 1 times the square root of the modulus of w squared plus 1. Now what I'll do is just try to evaluate this limit with some tricks I know about factoring. Okay, this is the same as trying to evaluate the limit as w, the modulus of w goes to infinity, of 2 times the modulus of z divided by w minus 1 times w, right? Just factor that, okay? And I'll do the same type of trick on the bottom. plus, put it right here, yeah. 1 plus 1 over modulus of W squared times modulus of W squared. Right? Now remember, the modulus of a product is the product of the moduli. Right? So what do we get here? We got 2 times the modulus of Z divided by W minus 1 times the modulus of W divided by square root of the modulus of Z squared plus 1 times the square root of 1 plus 1 over the modulus of W squared times the modulus of W. I pulled the modulus of W squared out of the square root.
What did you write on the top? So it's 2 modulus of Z over W minus 1.
Modulus times the modulus of W. Okay? And then I have a copy of the modulus of W in the denominator too. They cancel. Okay? Two times modulus of Z divided by W minus 1 divided by modulus of Z squared plus 1 times square root of 1 plus 1 over the modulus of W squared. Okay, now, what does Z divided by W go to in modulus? I'm sorry, this is infinity, not 0. This goes to 1 in modulus, right? So we get, I'm sorry, yeah, that's right. This goes to 0 in modulus, is what I mean to say. So we're taking the modulus of negative 1. So we get a 1 in the numerator. Okay? Likewise, 1 over the modulus of W squared goes to 0 as the modulus goes to infinity. So we just get a square root of 1 here. So our limit is just 2 divided by the square root of the modulus of Z squared plus 1. This is the definition of the distance from the complex number Z to the point infinity. It's the chordal distance. And you can verify this geometrically. Right? Just draw a sphere, take the equatorial plane, pick some point on that plane, and then calculate the distance from that point to the point 0, 0, 1. You should get this. Okay? Sorry, I went over a couple minutes here. But I'll see you all on Friday, and I promise I'll have the assignment 2 ready for you. Yeah.